Hey, what's up? We're back here again in Mr. Knight's class, and we're ready to just move on to video 3. This is going to be video 3 right here. Thermochemistry number 3 for night chemistry. You know it. All right, so let's pick back up where we left off with the notes. I'm going to pick up right here. Where we left off was labeling each of these steps along a heating curve. In this case, we could apply it to water, which would be the last problem on the other worksheet. And it's okay because we're going to improve here along the way. Even if you missed it one time, you won't miss it the second time because it might be on the next activity for today. Or the earlier today, I guess, Tuesday's class. So this is going to be homework, of course, Tuesday night for you to watch this video. Video number 3. So we have Q equals MC delta T for this section. This section does not have a temperature increase. So by nature, it is instead going to be a heat based on a phase change, a heat of fusion in this case. So we have Q fuss equals mass, again, because the mass matters, times some constant. In this case, it's L fuss. Then section CD, we have this section is Q equals MC delta T. Then the top section is Q VAP equals M times L VAP. Now I want to point out here that L and H are interchangeable here. L fuss or VAP is the same as saying H fuss or VAP. That's the heat of fusion, the latent heat of fusion or heat of fusion, latent heat of vaporization or heat of vaporization. Anyway, that becomes the other constant to multiply by, mass times that. And I can show you that a table of those. That table has to be given to you. Notice we have on this table, we have heat of fusion and the latent heat of vaporization. It gives it to you in kilojoules per kilogram, but if we just take away the kilo on both of them, we can do it equivalently to give you some joules per grams of some major ones. Of course, Coach McLean came over in here and put his name on. I'm going to get his name on his YouTube live, I guess. I don't know, or this video. So here we go. Let's continue on from there. Oops. Let's continue on through the slides. Remember, that gets us through charting the course here, and of course the last Q value would be that Q equals MC delta T. And that's the newest thing we just added in from the last video was the latent heat of fusion, calculating the Q for a phase change depending on without temperatures. Doesn't depend on temperature because there's no temperature change. The temperature remains constant during a phase change because things are balancing out. The speed that particles possesses balancing out. So you have Q fuss and Q VAP. We can find those heats each out for those parts using the latent heat of fusion and vaporization constants. So moving right along, I want you to go ahead and get out a sheet of paper because we're going to cover a period of this. And we're going to actually finish this in the next part of the unit, which is the kinetics and rate, reaction rate section of the notes. So go ahead and get out a sheet of paper, and on one side, split the top and bottom half into Q&A. Let's see, do I have a blank sheet in front of me? No. Let's do the top half. Will be Q&A on top, and on the bottom, put energy diagram. And then when you flip it over, we're going to make it landscape style. So we go portrait style first, flip over, and turn sideways, and you get landscape style. And you break into 4 boxes: equilibrium, Le Chatelier's, equilibrium constant, equilibrium conditions. Go ahead and make that sheet of paper. All of this back stuff and the front Q&A will be filled out in the next section of notes. But we're going to fill out the energy diagram first thing. That's the bottom half of the front piece of paper. Pause right now. Get that done. Go. Do it now. Make sure your sheet of paper looks like that. And then you can restart this video. Neat. Let's keep going. So energy diagram, this is what you put in there. You sketch it as is. We show in this energy diagram, it demonstrates how energy is charted over the course of a reaction here. Let me actually mark this. shows energy over the course of a reaction. Oops, get out of there. Over the course of the reaction, and so we're going to plot this as reactants turn to products is essentially what this is going to demonstrate. So show the energy actually hits a bump, hill of some sort, and then it has a lower energy state. Notice the reason why this is working out is, in this case, is that it happens to work out and works well, is that there's the energy of the reactants is higher than the energy of the products. So there's this net loss of energy, right? It's a negative loss of energy. A delta AE has been lost through this reaction. Of course, this makes it negative. This is exothermic, which you are familiar with a little bit. But we're going to finish labeling this graph. You got to make the curve to it. Pause if you need some time. And here's some lines just to delineate the beginning, where the reactants are, the tippy top, what actually happens in an activated state, and then finally where the products are in the energy line, which create a little dotted line over there. Label the reactants and the products there. And then we have this activated state. It's called the activated complex. It's where the reactants are basically in a mode of collision, and they're at a high energy state. It requires a lot of energy to actually get them to that state, that type of collision. It's got to be the right orientation and conformation, but they collide, where elements collide, molecules collide. They reach this activated complex. Reactants that will turn to products through a reaction. When they collide, they reach an activated complex, which they need a certain amount of energy. They have to hit an energy threshold. They have to receive enough input energy to reach that activated complex. Notice the rise in energy. So that the reaction will proceed, and it just, once it overcomes that hump, it proceeds downhill. Once the activated complex is reached, like the blade of a knife, it just folds down the other direction here, and proceeds through to form the products. The reactants transform into the products itself without destroying any mass. But they sit in that activated complex. They have to overcome the hill of energy required, called the activation energy. Notice energy, subscript A, that means energy activation. So worth pointing out. Make sure you have that in there. That is an exothermic reaction. Don't let that take up all your space. You're going to want to put also the other side on the other type of reaction, endothermic, in that same section of the energy diagram, just to be able to compare. You can label this one exothermic. In case you already used up all that space, that's okay. You can make the next one smaller. It's going to be self-explanatory as we go. So, activation energy, let's watch this.
If oxygen and methane molecules are mixed together in the same container, they collide. But there is no reaction until a spark or flame is added. Why? To react, the molecules must collide with sufficient energy to break the oxygen-oxygen bonds and carbon-hydrogen bonds so new bonds can form. The additional energy needed to break existing bonds and start the reaction is called activation energy. An energy diagram can help show these energy changes. Initially, the oxygen and methane molecules collide but do not have sufficient energy to react. A flame can supply the activation energy needed to start the reaction. At this point, bonds break and new bonds form in an exothermic reaction that releases energy. The energy released supplies the activation energy for other molecules to react, and the mixture explodes. In the air, nitrogen and oxygen are continually colliding, but lack sufficient energy to react. Heat from lightning supplies the activation energy to break bonds, and new bonds form in an endothermic reaction that absorbs energy.
Nice. Pretty interesting stuff going on there with the exothermic, endothermic reaction situation. Hopefully that wasn't too echoey. I hope this didn't create a volume issue. I guess I could have made sure of that. But anyway, that video I might post separately just to be sure. That is exothermic and endothermic. Notice the endothermic actually has a higher energy state in the products. So let's keep going. Exothermic, we've already seen this. You can add this label. You can add this label to your exothermic reaction diagram, energy diagram. Notice they've already labeled also the energy of the reactants and products, but they label them reactants and products. So did we. Notice this delta H means less energy in the actual system. So the system releases a delta H value. Therefore, it's lost. It's a negative value. Then So we would say, we depict this reaction to say reactants yield products plus energy. You've probably seen this already on a couple of the practice problems on Solidus Realize. So exothermic means exiting substance, which means products have less energy than reactants. Surroundings get hotter because the system gives off that delta H value. That's negative H. That means it's heating up the surroundings from the system. The system loses it, the surroundings gain it. Combustions are always negative, are exothermic. Thermite. Hand warmers are exothermic. This is versus cold packs. Oxidation reactions also do this as well. This would be things like metabolism as well, breaking down of sugar as exothermic. This is why you heat up. You actually, it's not always discernible when you eat food, you actually heat up a little bit due to the exothermic reaction of metabolism breaking down your food, or catabolism. Anyway, so there's some demos can look like this, or excuse me, some reactions can look like this. If we were in class, I'd do the demo here. As calcium can, when dissolving, always is an exothermic reaction. They get warmer as objects dissolve, like calcium chloride dissolving in water, sodium hydroxide dissolving in water releases this energy on the right side of the reaction, normally given to us in some sort of number in kilojoules. There you go. And we can do this kilojoules. We can relate this kilojoules to the number of moles as this coefficients in here. So we would say kilojoules per mole. And you've probably seen this calculation made a lot of sense, that if I had, instead of 1 mole, like the formula units show, 1 mole of CaCl2, if I had 3 moles of CaCl2, I could multiply this kilojoules per mole times 3, and I'd get my kilojoules produced, but by the excess number of moles. So worth a second look there if you need it. Endothermic, of course, takes your reactants and your products and requires the same input of energy to get it up over the hump, called the activation energy. Make sure you label that. We labeled it as EA earlier. EA, okay? E subscript A is the activation energy. And then we noticed the products are at a higher energy state than the reactants. So they absorbed and kept some of that activation energy. And don't forget to put up here the activated complex. Activated complex is up there, normally represented by the reactants really close together as if they're colliding, and an asterisk, which just means they're an activated complex at that point in time. And then they immediately proceed to the product side, but they retain some of the activation energy that was put into it, and then stored bonds of the new products that have been formed. So endothermic reactions absorb the heat. Neat. Heat entering the substance. Products have more energy than reactants. Products have more energy. The surroundings therefore get colder because the system absorbs a delta H. There's a positive delta H, so that absorbs the heat. So the surroundings feel the loss of heat, which would be cooler. Instant cold packs do this. There are several different examples of baking of foods. They absorb the heat to transform their inside bonds and products and things like that. Of course, they undergo some other reactions to release that heat again, because it's not all stored in there as forever energy. Some of that heat doesn't actually transform the bonds. It's kind of remaining and it exits out. There are some other examples, like from the Savas activity we did yesterday, that are worth taking a look at. The way this looks to us is that NH4Cl has or in this example, we have energy towards the inside, on the left side, the reactant side. I think earlier I might have said that the solutions are always exothermic. That's not true. Solutions always change the energy. When things dissolve, that changes the energy amount. There's heat related to this. That's this delta H heat of solution is often a number that can be given as well. Now, in this case, endothermic means energy is on the inside, on the reactant side, absorbing in heat, therefore producing new products with less energy, okay, or producing new products with more energy, and therefore colder surroundings in this case. Okay, so this demonstrates how the reactions can be written. And of course, that could be a delta H value in also kilojoules, or simply joules, but it's normally kilojoules as the amount of the H energy as a reactant side. So we look at energy flow as we move along the phase changes. We say energy is added from solid to liquid to gas, melting, freezing, vaporizing, condensing. And then, of course, we talked about endothermic means endothermic means energy is absorbed in to turn a solid into a liquid, into a gas, of course. And then in the reverse is exothermic, which is kind of hard. It's kind of a misnomer because you think liquids becoming solids. Wait a minute. Liquids becoming solids, that means things are getting colder. The surroundings are not getting colder. The system gets colder by slowing down, which means the system itself is getting colder, solid, the ice itself, but it's releasing heat. That's an exothermic reaction, so that's fun. While water freezes into ice, it is getting colder, of course, but it releases heat energy. And you can exemplify this heat energy because when you touch the ice, it feels cold because it's lost so much heat in its formation. So that's kind of what you could say. Replay that back. We can apply that Q equals MC delta T to the equation again. Exothermic, endothermic reactions. Make sure you have this picture, of course, at the bottom of that energy diagram page. If you didn't now or at the time, pause now. Make sure this graph is also inside. Don't forget to put the asterisk up there with activated complex. And of course, the delta H. Make sure you have that on both graphs. For endothermic, it's up, and for exothermic, it's on the downside. Let's get it after it. So quickly, let's do some quick practices. Endothermic or exothermic? Fireworks. Exothermic releases heat energy very fast. And once again, with exothermic, you're talking about one reaction releases energy, and the released energy can actually become the activation energy of the next set of molecules. So this creates chain reaction or explosions. If that the exothermic causes one reaction to power two reactions, then those two reactions create enough power or energy to power two more reactions, and so on and so forth. That exponentially causes more reactions. And if those reactions happen very rapidly, that's called an explosion, thus exothermic. Ice cold packs, that means heat's going into the cold pack as a system, endothermic. Ice melting in this case. The ice absorbs energy, that's endothermic. Pause after I say the thing. I'll do a quick pause so you can have a moment to do it. Pause if you want to try to answer before I show. Condensation, this is vapor forming liquid on the can of a cold can here. That would be cooling, which means exothermic. As it goes towards the liquid range, it's cooling. That means it releases heat. It cools, releases heat. It warms up, it's absorbing heat, right? Okay. Freezing, it's cooling, therefore releases the heat, that's exothermic. Boiling, the water is absorbing the heat, that's endothermic, to turn it into liquid or vapor. Excuse me, and let's see.
Hi, I've got a couple of demos loaded up and ready to go, and one of these is
let's see if we can watch this video here.
going to go ahead and give off heat, and the other one's going to have heat taken in. So I've got a beaker of water at room temperature. The red display shows that it's near 20 degrees C room temperature. And I'm going to lower the temperature, and I'm not going to do so electronically like with a freezer, and I'm not going to do it with ice. I'm going to dissolve a solid, which is actually going to promote an endothermic process. The solid is called ammonium nitrate, and I have the formula on the board, and I'll point that out to you in just a moment. What's going to happen is water molecules will surround this, and the reaction actually sucks in energy. So we're going to see a nice little temperature decrease here. So as I tap this in and it's stirring, we're going to see the temperature decrease. So on a good day, it'll drop down to about 0 degrees C. So it looks like we've got 7, and it's continuing to drop. The driving force for this reaction is the dissolving. The ammonium and nitrate ions are being surrounded by water, and it's going to a state of more disorder, as we say, and it's making the reaction happen. But in the process, think of it as like an energy vortex. Heat from the outside, heat from the water are sucked in to make the reaction proceed. Oh, and very good, it keeps dropping at 5. There aren't too many of these reactions, so this is rather novel. I also give it the nickname of the cold pack reaction, because these first aid cold packs, these little plastic bags with an inside bag, are available at pharmacies. And what will happen is if somebody bumps themselves like in the playground, somebody might come running over with one of these cold packs. What they do is snap it, and it's mixing the water on the inside with the ammonium nitrate, and it's spontaneously going cold, as demonstrated. Another little process loaded up here is just a simple combustion. I have some methanol, which is a 1-carbon alcohol, and I'm going to spray some on the counter and just go ahead and light it on fire. And flames are given off, a sign that we have heat, and I'll give personal testimony. It's warm. We have yellow, orange, blue flames here. It's combusting, heat's given off. That energy that's given off as heat came from chemical energy to begin with. Bonds are being broken, which costs energy, but then new bonds are being made and energy is being released. Let me go ahead and show you the processes up here on the board. The left side is the first reaction, and that is the cold pack reaction. The ammonium nitrate is a solid, and it's mixed with water and becomes ammonium nitrate aqueous. So these are two separate ions. NH4 plus is floating around, NO3 minus is floating around in the water. And at the beginning here, call it a baseline or the before enthalpy or heat, this is done at constant pressure, is around here. And what's happening is it's sucking heat in from the environment, from the water and the air. The analogy might be something like your checking account, where checking account starts here, then it's payday and a deposit is made. Ooh, that's nice. We increase the heat of the system, or the enthalpy, the heat at constant pressure. The time axis is simply just showing before and after. I have an arrow here going heat is taken in, so the energy of the system rises. Endothermic, or entering heat, heat enters the system. On the right side is that combustion of the alcohol. CH3OH is methanol. It burns in oxygen in the environment, and then we produce carbon dioxide and water. We start off with some high energy bonds, and then we end up with basically waste products, carbon dioxide and water. When you exhale, carbon dioxide and water come out. You extinguish candles with this. We use these in fire extinguishers, very low energy molecules. We start off high, we end down low. There's a little bit of an activation energy at the beginning, that hump that we have to get down over. Heat is given off in this process. Exiting heat, exothermic. What I'd like you to do is think about the delta H values for these two. One is going to be positive, one is going to be negative. Which one do you think is positive? Which one's negative? Have a look at the plots. See what's happening to the energy of the system. I wrote down that our endothermic is positive. We have an increase in enthalpy. You can see the before and after case.
And the exothermic is negative. I think we get the picture there. So we're going to move right on to the next portion of these notes. Burning the candle, endothermic or exothermic? It is exothermic. Once again, if I say it or I show it, you can pause, try to guess, and try yourself first. Nuclear fission. Exothermic, a tremendous amount of energy release. Cooking an egg. Cooking anything for that matter. Endothermic. Formation of a salt, sodium chloride. You got plus 411 kilojoules on the which side? Product side. That means exothermic. Water evaporating. Going from liquid to gas. The water had to absorb energy, endothermic. Carbon dioxide sublimating. This is going from solid to gas. Taking in a lot of energy all at once. That's endothermic as well. Gas to liquid. This is the gas cooling. So it's releasing energy to do so. Exothermic, so that it can cool. Photosynthesis. Notice right here, this might be a little bit more hidden, but we have sunlight is a type of energy, and it's on the reactant side. That's on the in part, endothermic, the inputs. Over here, we've got 483 kilojoules on the product side, of course. That's exothermic. Combustion. Notice the product side yet again. This is what he did on the countertop. Exothermic, thus fire. Lots of energy actually for a small bit of stuff. So there you go. So summarize the following terms with your neighbor if you need to. Or if you do it with your cat, your dog, your pillow, that's fine. Or a parent or guardian, take a look at it and see if you can remember those terms. And let's go. Go back and pause and do it if you need to. Okay, remember a closer look. Phase diagram, that's one phase diagram. This is another phase diagram which also takes into account pressure versus the temperature. And we see that there's this triple point that actually at the right pressure and temperature, the substances can kind of be like a triple thing. It's a triple point. We're going to act like all of the matter at one point, and it kind of cancels out. And then, of course, you have up here this critical point where you have such a high enough pressure and or a high enough temperature that it ceases to be a solid, liquid, or gas. This is the fourth state of matter, this plasma, also called supercritical fluid, which is just cool to talk about, cool to say in general. Supercritical fluid is above the critical point. And, of course, oops, let's go back. This one shows the phase changes as well, and that liquid and solid and gas are not so far apart as they appear on the other phase change diagrams. So worth pointing that out. We've got all the things to worry about. This kind of gives you some of the topics that we've covered to this point. Take a look at them, think about them if you will. This is how things may have gone in a different circumstance had we not been where we are. Nevertheless, some other review items you can pause, take a look at those, read those on your own. They're all review type stuff. Q equals MC delta T, how it applies the heating curve. You can go look at that problem as well. It's another practice of the specific heat. Of course, it shows you the energy. So pause now, practice it if you'd like. Keep on going. Neat. Now into the next unit, 17.7. This is going to touch on latent heat in greater capacity, especially heat changes of state. And this is really just me. I'm just going to slide through the slides as much as I can. And this is just straight from the textbook. I'm going to try to summarize some points, but mostly I want you to go back through. I want you to read these pieces. They are on the slides on Google Classroom. If I'm incorrect for some reason, you go take a look. But honestly, we just want to be thinking about these different circumstances in various capacities. I'm just trying to put that information out in front of you without making this video too long, of course, because we're already approaching up on some higher end numbers. Anyway, heat and changes of state. What does sweat help cool? Why does sweating help cool you off? Turns out the liquid, as it absorbs heat from your body more, it evaporates into gas, carrying the higher energy heat away from your skin, and therefore, so you sweat as it's liquid. It's not cooling you off, but as it turns from liquid into gas is when it actually cools you off. That's why you feel colder. What's the relationship between molar heat of fusion, molar heat of solidification? They are opposites. Fusion turns solid into liquid. Solidification goes liquid into liquid into solid, back again. They are opposites. This opposite points out an interesting thing. The gain of heat causes a change of state instead of a change in temperature. This is when the flat lines of your heating curve, temperature remains constant throughout that process. Pause those things if you need to read that again. This is a rehash of the heating curve that I posted on there already. This is a rehash of essentially this concept right here, or this one in greater detail. Mainly these notes are focusing on these Q equals ml fuss and Q equals ml vap. Also H fuss, H vap are replaceable for those terms. So just so you're not confused, this is in fact right on par. We just talk about molar heat of fusion would be that solid to liquid phase. Molar heat of solidification would be the reverse of it. Pause if you need to take a look. Maybe write those definitions down if you feel like that's something that doesn't ring a bell with you. Quantity of heat absorbed by a melting solid is exactly the same as the quantity released when it solidifies. In other words, H fuss and H solidification are equal, but they've got that opposite sign going on, and that's kind of the key point to remember. So melting of 1 mole of ice at 0 degrees C to 1 mole of liquid water at 0 degrees C requires the absorption of 6.01 kilojoules of heat. The conversion of 1 mole of liquid to 1 mole of ice releases 6.01 kilojoules. So this is absorption of 6.01. This is releases 6.01. And this just shows here how they are opposite but equal in value, opposite in nature of that reaction. So using it in phase changes, we have how many grams of ice at 0 degrees C will melt if 2.25 kilojoules of heat was added. Well, we've got our initial final temperature. It doesn't change there. And then our H fuss is in a kJ per mole. Now, we're used to using kilojoules per gram or just joules per gram as another L latent heat of fusion equation. That's what this chart is all about. This is all latent heat of fusion in joules per gram, also kilojoules per kilogram. They mean the same thing if you get rid of the kilos in both. Latent heat of vaporization, same situation going on there. This constant, however, is given to us in kilojoules per mole. Let's pause and think about that for a second. The difference between joules per mole and joules per gram, or kilojoules per mole. This just means 1,000 joules per gram. Of course, kilojoules means 1,000 joules. So if we plug in this into the formula, Q equals M delta H fuss, this delta H fuss is kJ per mole. That means this is actually mole per mole times H fuss, which means this number is not an N, this is an M, this is an N, which means number of moles. It's just a slight variation of the equation before. Our equation before is Q equals M L fuss versus this equation is Q equals N delta H fuss. And that's because this one is in kilojoules per mole, and this L fuss is in joules per gram. So this is just the units are different. Nevertheless, depending on what they give you, if they give you joules and they give you grams, then you need to be in joules and you need to be in grams. If they give you kilojoules and moles, then this number is going to be in moles and this number is going to be in kilojoules. Just follow the units, match them up, make sure they work. Usually it's just 1 or 2 step simple math here. So in this case, we're going to use the other equation where we've got the Q, or excuse me, actually they're calling the QH, they're using it the delta H. Delta H equals N times delta H fuss. So we have 2.25, and then we have the 6.01 number. Divide the 6.01 number into the 2.25. 2.25 divided by 6.01, and we get the mass, or we get the moles divided. That gives us the number of moles. Of course, the molar mass we have to take into account to get it into the mass value because the question wants an M. So we have to convert our mole answer into mass by multiplying times the molar mass. Multiplying the molar mass, dividing by 6.01, which solves the equation, gets us our mass at 6.74 grams of H2S, which is solid. To melt 1 mole of ice, therefore, we got to just see if this makes sense. We're saying to melt 1 mole of ice, 6.01 joules is required. That's just stating a factor. If we have about a third of this amount of heat, 2 kilojoules, about a third of 6 kilojoules, then only about 1/3 of mole of ice would melt, which is about 6. So the estimate's close to the calculated answer. Pause and reread if you need to, if that was a little confusing, as needed. Okay, let me just shift a little bit. Cool. Calculate the amount of heat absorbed to liquefy 15 grams of methanol at the melting point. If the molar heat of fusion of methanol is 3.16 kilojoules per mole. So we're going to find the amount of heat absorbed. Heat is that delta H value, or also the Q. So we're going to plug that into the N times this kilojoules per mole value, the H fuss. But first we need moles to find Q. Number of moles, well, we have grams. Convert grams into moles. And then we plug it in, multiply the 2 numbers, and we get Q. Bottom line is this. Mass to moles times the kilojoules per mole, because it's 1 mole to 1 moles cancel there, and you get 1.54 kilojoules of Q heat is released. So, everybody good? Everybody kosher on that one? I would think so. Pause and go back if you need to. This is just another calculation involving a simpler equation, really. Really and truly, this is just heats of changes of states. What are the molar heat of vaporization and molar heat of condensation? Those are also opposite each other. We have the boiling point. Okay, this is where the substance goes from liquid to gas. That's through the vaporization. Here's a chart of delta H of vaporizations and comparing them to fusions in kilojoules per mole. So worth a second look there. Of course, Just understand those are some important values for us. Table lists them at their normal boiling point at that 100 degrees Celsius in terms of, well, or at whatever the boiling point is for each of these substances. Water is 100 degrees Celsius. So what is molar heat of condensation? Is the reverse of vaporization, exactly the same as fusion to solidification are opposites. So is vaporization to condensation. So why evaporation of sweat off your body helps cool you off? Because that liquid turning into gas is being vaporized, absorbing heat from your skin and carrying it away. That means your skin loses that excess heat. Pause and read if you like. Heating curve graphically can show the enthalpy changes that take place during all the phase changes. Solid, liquid, gas. This is just a reiteration of the exact same picture here as what we did here. And then that problem number 9, which was number 15 also. There's number 9 in our set. There's number 15 from the textbook set. That's what's shown right here. This is just a reiteration with the H's in place. How much heat is absorbed? In this case, with this many grams, 100 degrees C, at this pressure, converted to a gas, 100 degrees C. Lots of excess information that we don't really need. We know our initial conditions, which just means that our formulation will work. It also means that we can look at the this HVAP from the table earlier is useful. So really and truly, we just means this information just says, hey, look at the graph, or look at the table of information that you've already referenced once. Okay, we have mass. And of course, same equation is moles times kilojoules per moles. So we have got to convert to moles. Then we do times the kilojoules. So convert to moles times the kilojoules, which is our HFUS or HVAP there. And then we multiply, we get our answer in kilojoules. Pause and take a look at how the units cancel for that purpose. Knowing molar mass of water can be estimated less than 1.5 moles. In this case, does the result make sense? Take a look, read it, make sure that it makes sense to you, pause it, and then we're going to go. This is just an estimation thing, like to relate to your answer. Does it critically thinking make sense? Molar heat of condensation is the same in the magnitude as which of the following? Same in magnitude, but not necessarily sign. That would be, molar heat of vaporization. Cool. What thermochemical changes can occur when a solution forms? When a solution forms, heat can either be absorbed or released. Replay that if you need to. Enthalpy is changed as the molar heat of solution. This is called delta H solution. Pause and take notes if you need them. Practical application, of course, is the exothermic process of a hot pack. You crack that thing open in the first place, and it starts immediately reacting and releasing heat as the solution is made, even though it's not necessarily there's very, very minimal water. The water in your hands actually generates that. A lot of times it's absorbed a little bit. Makes it negative kilojoules per mole, and that allows to warm yourself. Dissolution of ammonium nitrate. This is what was shown in the demonstration video that guy was showing. Cold pack is ammonium nitrate mixes with water. As it dissolves, it actually absorbs some energy, and that's where you get that cold pack. It's absorbing heat, therefore cold. How much heat is released when 2.5 moles is dissolved in water? Well, we're going to need some the heats of dissolution or heat of solution for NaOH to find that. So we know that the heat of solution is negative 44.5 kilojoules per mole. That has to be given to us either from a data table or granted to us in the problem. Then we know the amount that is moles in this case. This is the same thing. We got to get rid of moles on bottom, so we got to multiply by moles in order to get that delta H value. Kilojoules per mole. Moles times the top number divided by 1 mole cancels out our moles, and now we're in kilojoules, which is the units for a delta H heat or Q. Slow this thing down a little bit. Read this again if you need to. Make sure it makes sense to you. Let's go. Another practice problem. Pause and read it and try it on your own. 50 grams. Got to convert it to moles times the kilojoules heat of solution, and you get your answer. Quantity of heat absorbed by melting is exactly the same as quantity of heat released, or by solidification. Vaporization, opposite and equal to condensation. Heat formation of solution heated can either be released or absorbed. The values of heat have to be given to you and simply multiplied. There, once again, is a summary of all of the terms. pause and get those if you didn't already, or if you need to already. Some more terms there, and go dogs. That's the end of chapter section 17.3. The last one would be heats of reaction, and I'm actually going to put this into a second part, so I'm going to pause and end it right there. Go dogs. Good job on part 1. It's been a long bit, and I've been talking a lot, and a lot of slides we just got through. Go look at the slides yourself online, and I promise they're a lot easier than you think. Go dogs, and we'll keep it up tomorrow.